But okay, then it's 5. I would start then. So welcome everybody to the sessions on tools and environments. We have 6 talks. We will do that in the first half an hour, and then we will leave the second slot of this hour we have together for questions. So while the authors are presenting, I would encourage you to write your questions in the chat on the right, exactly here. And with that, I would like to introduce the first speaker for this session, who is Colin from Drexel University, and he's talking about towards property-based tests in natural language. This is a paper in the NEAR track, and the stage is yours.
All right. Thank you. So let's get to it. So I've been thinking for a while now about this problem of natural language specifications, right? So this is kind of a long-standing ideal in the software engineering research that we'd really like to be able to just describe the expected behavior of software, whether this is unit test or top-level spec, in terms of a natural language. And of course, this worked 20 minutes ago and is now not rendering correctly. So let's see if we make this a little bit easier. All right, a little less pretty, but it will work. So this is a fundamentally hard problem. So there's all sorts of reasons this is a hard problem. But, you know, one of them, one of the most prominent is basically, all right, this open vocabulary problem. The problem that in general, there's going to be new words or customized word meanings in every new problem domain, every new code base. So this has been tackled before with things like template-based techniques, but those, of course, have limits. Right? So these are things like regular expressions. They can work really well in some domains, but unfortunately, this can make the specification language very brittle. It can make expressing certain things kind of difficult. So we throw machine learning at it, right? Well, you can, and other people at ICSE this year have some cool work that does this that you should check out, but this is not what I did. So what I did was borrowed some techniques from classic linguistics, because the traditional machine learning models end up being hard to repair, hard to extend. They need massive amounts of training data. So, oh boy. Linguists have spent a long time building rich formalisms for dealing with compositional semantics. So basically, studying ways that sentence meaning is built up from individual word meanings. And there's a large family of techniques for this called categorial grammars. Sorry, I'm going to try to move my slides over here and see if this renders slightly more correctly, which it, of course, does not. All right, I'm going to try to redo the screen share. And see if this gets better. All right. So categorial grammars is one of these linguistically motivated approaches, which has been used extensively for deep studies of all sorts of natural languages from all kinds of language families. And for our purposes, something that's of interest to us is the fact that their notion of meaning for individual words and sentences is basically a lambda calculus with something that kind of acts like a Boolean. So it's a functional programming language, which is a good fit actually for property-based tests, which in their traditional formulation are basically expressed mostly with higher order functions and functional combinators, and end up generating test specifications that look like, for all generated inputs, this thing is good. And so if you actually look at this from the perspective of classic linguistics work, this actually looks a lot like classic denotation of something involving a quantifier in natural language. So we can take this idea and we can build on it, right? So in particular, we can pick up some of the base logical inference rules from these categorical grammar systems, like these are two out of a number of them, that deal with if you have two sentence fragments, gamma and delta, that have grammatical types that maybe say that one of them is looking for a particular kind of clause to its right or to its left. If you put them next to each other in a sentence in the right order, you can combine them and get the expected grammatical type, but you can also combine their semantics, which in this case is simple function application. So if you put these logical rules together with a large enough lexicon, basically a database of, for each word, what are its acceptable grammatical rules and semantics, you end up building essentially derivations in a logic that witness that certain natural language utterances parse and have certain semantics, like every even integer is odd is a valid sentence with, as semantics, this property-based test, which happens to fail, which is important because we need failing tests in order to find bugs. So I took this idea and I ran with it. I built enough of a lexicon to tackle the examples from a property-based testing chapter in a draft textbook, made a couple mild simplifications, parsed the result using my lexicon, but an off-the-shelf categorical grammar toolkit, and then transliterated that AST for a property-based test into JavaScript to run them. So what did I find? Well, 3 out of 7 tests were actually correct translations, but the tests failed because they were underspecified. So this particular case, it was a textbook, so this was probably on purpose to keep things simple, but this is very similar to what happens in unintentional cases of underspecification as well. I took a look at whether there would be grammar restrictions that might cause problems if we try to build on and extend this idea further. So I took some existing grammar-only categorical grammar databases and dug up a bunch of other property-based testing examples, and they all parse just fine. Ended up actually connecting to some results from linguistics on mathematical text, because it turns out certain words get overloaded with multiple denotations, for example, whether they're being used to generate input or check properties of input. And I was able to actually take advantage of being able to extend or fix individual words by basically changing individual lexicon entries, which is something that you can't do with most machine learning techniques today. So I'll keep working on this for tests and a little bit for proof assistance, and thanks.
Thanks a lot, Colin. Then maybe the next speaker, Marcus, you can start sharing your screen. So Marcus, he has a double affiliation, both Siemens and LMU Munich. Is that correct?
Absolutely, yes.
Okay, and he will talk about using a semantic knowledge base to improve the management security reports in industrial DevOps projects.
Okay.
And the stage is yours.
Thanks a lot. I hope you can see my slides, but I guess so. Okay, so thanks a lot. Welcome to the virtual presentation of this paper. We added this paper at the SAFE track. So for the presentation itself, we will look into 3 questions. Why did we do it? How did we do it? And also, what do we do with that now, with that knowledge we have here? As a little background where we came from with that topic, actually we started with the topic of security automation. So trying to automate security activities like testing, scanning, checking, and so on in pipeline stages, meaning also with different types of products or product stages. And we noticed there that actually in practice, we have some issues with the security feedback loop. So how do we get the information that is now produced back to our developers, back to our project team to actually solve these issues? We had a look at existing approaches, existing tools there, but all of them lacked certain properties we saw as absolutely essential for our environment. So we had a look ourselves. First of all, looked into the problems. We found 3 major issues: the report content, which is more around every tool produces a different format, different type of language to a certain degree, also different perspective here, and is only correct to a certain degree. Utilization is different. So a developer requires a different type of information from these reports than a project manager or a customer. And finally, the interconnection between multiple sources. So in larger enterprises, you mostly have existing activities like threat modeling, some security champions or experts, vulnerability monitoring, and so on. And all of that must be included when you work with these reports. And in particular, we noticed that manually, this is just not feasible at all. So in our research, we came across semantic knowledge bases. So basically databases where you can infer new knowledge based on existing knowledge and some rules or a static ontology. We decided to develop our own, first of all, to see whether it could work like we imagined. Started with having some data storage, you see on the right-hand side, which stored our belief, so data, and the rules to infer new knowledge. We had an inference engine which does exactly this inference, a logical core which ensures maintenance, so everything should be maintained consistent, and a user interface, of course, to access this information. From a normal average knowledge base, we deviated a little bit. We had some specifications. In particular, we considered revisable belief. So not all of that stuff that's given by tools is correct. So we need to be able to revise knowledge. That's why we called it belief. It must be customized to each project, and it must be incrementally maintained if new reports arise. We noticed that most inferences are streamlined, and by default, every project needs inferences like parsing, deduplication, some enrichment, validation, and validation also of identification of false positives here, and of course also some prioritization. We tried this, of course, as well out and tested it in 3 industrial software development projects, which employed DevOps techniques. So the focus of this knowledge base is also DevOps techniques. What we noticed as advantages, it's actually reducing the effort for the project team quite a lot, in particular if they have a security expert in there. It improves the overview and transparency, and it feels useful to the project team, which was really important to us. Challenges, of course, also existent here. The biggest feedback we received is that it's highly dependent on the user interface, whether it's perceived as useful or not. So it should be easy, good integrated, and so on. And of course, also the effort and cost for the server this knowledge base is running on, as it's highly critical data, thinking about vulnerability reports and so on. Exactly. If you found interest in the paper, feel free to either read it, get in contact with me or my colleague Ulrich Schöpp. Yeah, thanks for your attention.
Thanks a lot, Markus. So let me remind everybody, you can write your questions in the chat on the right. So in the meantime, the authors can think about it. The third paper of this session is also a software engineering in practice paper, and this is by Emma, Lund University. Stage is yours.
Thank you. Okay, I hope this works. Okay, so this is the title is What's Bothering Developers in Code Review, and this is a short paper with the people here, me, Luke, Jürgen, Diedrich, and Christopher. Most of us from Lund University, Luke also from University of Cambridge. So the setting is code review, so I'll give a brief. I know we're a little bit after schedule here, but I'll be brief. It's about code review, so just to get your mind into this, if you imagine a setting where we have an author, Alice, typically she puts together some change, she sends it for review. We have some other, she picks a reviewer, maybe, and then that reviewer looked at that change, sends some comments, they go back and forth and they discuss in a code review tool like it's GitHub, Gerrit, GitLab, Fabricator, and similar tools. And then they, if everything goes well, they end up with something like, it looks good to me, and then Alice merges the change. This is the way typically it can look, but many times other things happen along the way. So for instance, it may take time. So Alice may wonder where's Ruth? What happened? Is she on vacation? Is she busy? And also root while reviewing a code change. It's a lot of you have a lot of questions. There's a lot of effort involved. What's the effect of something? Does this comply with our requirements and so on? And also sometimes you involve, and many times you have 2 reviewers and even more, and many times there can be many languages in the same change. So many different things happen in code review. So what we were curious about in this project here was to kind of look at the user perspective here, the developer experience. We've had personal experience of code review. I think it's a very interesting research area, and kind of thinking about how can we intervene in this space, introduce new tools. So, and specifically focusing on what's bothering developers. So what we did here is that we conducted a couple of 12 interviews with 2 multinational companies. And this short paper is about the initial kind of reading of these transcripts. And then we followed up with deeper analysis, which we'll present later in June at EAST. So at this stage, what we found was specifically one thing that sort of stood out. And that is that we saw that we had different reviewers taking different roles, and this would happen implicitly. So for instance, we had one software developer that would say something like this. They would typically look for coding conventions, the motivation for a change, while at the same time we could talk to another developer, in this case a software architect, who would not, and I'll read this one. I try not to go into too much detail when I code review because I assume that the code here actually works and that the tests are written and so on. Of course, I can see it in the review as well. So I mainly focus on making sure nothing has been removed and that information that would be received by the API is still there. So these 2 developers have fairly different perspectives on this change. So we think of this as them having different units of attention. So one, if we simplify, focusing on coding convention, while the other is focusing on API compliance. And that renders different questions, and it includes different needs. At the same time, they have these different perspectives, but at the same time, they have the same unit of analysis. So the extent to which you can modify the look of Gerrit or GitHub and so on is fairly limited. So, and the thing that we saw that was not something we expected, didn't expect a specific thing here, but one thing that sort of popped up over and over again was that there seemed to be some kind of mismatch here. So one example from another developer here is that if it's a very complex change or a change that I'm not very familiar with, then I usually check it out in my IDE. And then they get better highlighting and they can follow the code more easily. Those were very common things that we saw and over again for many developers. So to us, this sort of suggests that there's some kind of mismatch here. There's a bunch of questions not being answered in the code review tool. And since we're thinking about tool interventions, this seems to be an interesting space to explore further. So this mismatch here is kind of the early result that we saw here. And to summarize, it's basically what we're seeing here is that one size doesn't fit all needs in code review. Okay, thank you.
Thanks a lot. So the next paper is also from the software engineering in practice track. The speaker is Bart. He's talking about project smells, experiences in analyzing the software quality of ML projects with MLint. Stage is yours.
Yes, MLint, indeed. Let me see if still opening the slideshow still makes it work. Yes, it should still work. All right, so my name is Bart van Oort. I'm a software engineer and I was doing my master thesis at TU Delft when I was writing this paper on code smells and software quality in machine learning projects and in collaboration with ING's AI for FinTech Research Lab. Now, I'm just going to go through the same slides as I use in the video, but then 4 times as quickly. The basic idea is that machine learning and AI are really pervasive in computer science. It's used for everything from Google searches to dancing robots. But machine learning obviously isn't magic. It needs to be written and it needs to be gathered. And most people that do that are called data scientists. And those data scientists are mathematically very strong, but they don't have a software engineering background often. So programmatically, they're not very experienced with writing large, complex software systems. And productionizing software is already difficult in traditional software engineering, but especially in machine learning, it is extra difficult there's extra challenges of managing the data, managing the model, training it, and how you deploy it as well. And throughout the traditional software engineering, we have come up with a bunch of with a host of different software engineering tools to help with ensuring the software quality of your complex system. So anything from Git to Kubernetes to testing frameworks and static analysis tools and whatnot. And specifically on static analysis tools, we wrote a paper last year for the Wayne conference, the workshop on AI engineering and the prevalence of code smells in machine learning projects. And what we learned, besides a list of the most prevalent code smells in those in open source machine learning projects, we also learned that there are bad dependency management practices in those projects, and there was also low static analysis tool adoption. These don't really pertain particularly to code smells, but it shows that software quality, that code smells are only a small piece of the software quality puzzle. So I came up with the idea of project smells, which is basically a more holistic perspective on the software quality of machine learning projects, which concerns with deficits in how a machine learning project is managed. And I wanted, as I said, I was doing this for my master thesis, and I wanted to have my master thesis have some kind of a practical impact, which would be usable by practitioners to help improve the software quality of their machine learning projects. So I wrote a tool for detecting these project smells, oriented on the machine learning project best practices by SE4ML and Google's Rules for ML. And this tool is basically a simple command line utility to evaluate the technical quality of machine learning and AI projects that are written in Python. And it does so by analyzing the project's source code, the data, and the configuration of all the tools that are being used around it. Anything from version controlling tools to find code smells, dependency management practices, and whatnot. And I wanted this tool to be usable for data scientists and ML engineers, but also for ML practitioners that aren't very experienced with these tools and techniques yet, and also for ML project managers to see where they can improve their projects. Now, of course, designing such a tool and finding those project smells, defining those project smells as well is not easy. There were a number of challenges in there. The first being to map from the high-level best practices that SE4ML or Google's Rules for ML pose to actual practical guidelines. And to solve that, to try and tackle that problem, we explored the industry and the machine learning tooling ecosystem, and we used input from experienced machine learning engineers at ING. And the next problem there is the heterogeneity of the machine learning projects, as there are a bunch of different toolings and frameworks that you could use, which makes the project different. There's also the difference between the maturity of the project. So is it just in the early stages of development? Is it still a proof of concept? Or is it more like deploying in production tomorrow? That brings a whole difficulty there. And we've tried to tackle that with configurability of MLlint and the ability to specify custom rules. But really, it is still kind of an open challenge, and maybe something that that you all may have some ideas with in a discussion later in this time slot. But in the paper, we primarily focused on evaluating MLlint. So we had a bunch of research questions to see how these project smells fit the industrial context of ING. As well as what kind of what ML practitioners generally think of the differences between proof of concept and production ready projects, the benefits of tools such as MLlint as well, and the obstacles for machine learning practitioners towards implementing best practices. To research this, to answer those questions, we did a mixed methods approach. We had qualitative analysis of MLlint reports from 8 machine learning applications within ING, and we ran a survey with 22 participants, both within ING as well as public. Most of them were ML engineers. We codified all the results and deduced all of the key ideas. The results themselves split over three themes. The first being data version control. I have to say this is about a tool, DVC, not necessarily the practice of data version control. There are various ways for doing that, and there are varying degrees of version control that these ways of managing your data or version controlling your data has. But what we primarily notice is that there was a kind of a lack of a standardized tooling for dealing with these data dependencies. There wasn't like one specific way that people were dealing with these data dependencies. And on the topic of code dependencies, even though it was perceived to be very important for proof of concept projects and absolutely essential for production ready projects, the practices still differ between different teams and different projects. And we noticed also that there is a lack of a standardized and easy to use and as well as maintainable method in Python for managing these code dependencies. That also creates problems for the software quality of the whole project. Finally, for static analysis tool adoption, we noticed that there is a tendency against the usage of static analysis tools in the development phase. They're more used in the production phase. And that's generally what they generally find is that there's a high rate of false positives. And it's difficult to kind of configure the linting rules so that they don't give false positives anymore. It takes a long time. It's very difficult. It's a known problem with linters, but again, in machine learning, this is compounded by the fact that the data scientists don't have much software engineering experience, which means they don't necessarily feel like spending the time in configuring these tools. So we identify a need for context-aware static analysis tools, the tools that understand the context of a project, how what maturity of the project it is, what kind of tooling they're using, that sort of stuff. So in conclusion, we've looked at the concept of project smells, and as future work, it would be interesting to have a more formal definition, as well as look at the observable impact on software quality. We've looked at the perceived impact of software quality, but the observable impact of software quality would also be interesting. There are also, of course, a host of different new tools and new linting rules that could be implemented in MLint, such as making it more context aware or focusing more on ML-specific code smells. And of course, there is also value in educating ML practitioners in finding, getting to know more of these SE for ML tools and practices. That basically. Thank you for your attention.
Okay, thanks a lot. So the next paper is from the technical track. It's discovering repetitive code changes in Python ML systems. The presenter is Malinda, correct? From the University of Colorado, Boulder. And if you can share your screen, the stage is yours. Perfect.
Okay, I hope it works. And let me start my talk. Hello, everyone. I'm Malinda. I'm a PhD student from University of Colorado, Boulder. The title of my talk is Discovering Repetitive Code Changes in Python Machine Learning Systems. Researchers capitalized many applications of the repetitiveness of the software. For example, automatic program repair, which mine previous fixes and develop systems to automatically fix the similar bugs. Likewise, we have API recommendation systems, library migrations. So these are the two examples ways of exploiting repetitiveness of code changes. So even though these applications conceptually language agnostic, the implementations are limited only for few languages such as Java. So thanks to the rich ecosystem of machine learning frameworks written in Python, such as TensorFlow and PyTorch, there's a rapid growth of machine learning systems written in Python. Since the implementation of the applications that they exploit repetitiveness is limited to languages such as Java and C++, the Python systems do not benefit from these applications. Therefore, machine learning developers' toolset is far behind the toolset of other developers. There's a vast ecosystem of repetitive code analysis tools developed for Java. For example, TypeFact Miner. It mines repeated type changes in Java systems. Migration Miner, CPAT Miner, Refactoring Miner. All of these are examples of such Java code analysis tools. We have a vast ecosystem of such repetitive code analysis tools. These tools take source code as input and pass the code to AST and infer its results based on the ASTs. So none of these tools have been developed for Python, which posed a significant hurdle to conduct mining research in Python systems. It is not feasible to re-implement the tools from scratch to Python either, because it requires a significant amount of development effort. To overcome these challenges, we propose Java 5.5, a technique to adapt existing Java analysis tools to Python. It leverages the similarity of Python and Java at the AST level. While statement, for statement, method invocation, all of these AST nodes exist in both Java and Python. So we found that there is a 90% overlap in the both languages at the AST level. So Java 5.5 leverages this similarity. Using Java 5.5, we adapted state-of-the-art Java code change pattern mining tool, CPAT Miner, to Python. And then to improve CPAT Miner and make it refactoring aware, we adapted the Java refactoring inference tool, Refactoring Miner, to Python. And then we integrate with CPAT Miner as RCPAT Miner. RCPAT Miner mines version history of Python systems in refactoring aware manner. To analyze the repetitive changes in machine learning systems, we first collected highly rated 1,000 machine learning systems. Then we executed RCPAT Miner on the commit history of all of these machine learning systems. Running RCPAT Miner on 1,000 machine learning systems produced 28,000 fine-grained code change patterns. As the next step, we performed thematic analysis on the top 20,500 patterns, and then we surveyed 97 developers who performed those patterns. So this slide summarizes all the results. We validated to evaluate the Python adapter refactoring miner. We validated 2,062 refactorings reported by Python version of refactoring miner, and it reported 95% precision. Our improved CPAT miner reported 50% more code change patterns and statistically significant more code change instances per pattern. Then we analyzed the top 20,500 code change patterns reported by the RCPAT miner. And then from our thematic analysis, we found 22 code change themes in Python that frequently happen in Python machine learning systems. So this code change is the code change in these slides represent one such example theme. So where the developer transformed the for loops to NumPy. The APIs in NumPy. NumPy is a Python highly optimized Python library. So developers are transforming their language construct to the language APIs in NumPy. So it's a one theme that we found under that belongs to 22 themes. So we have 22 such code example themes. So you can find all of them in our paper and in our companion website. So as a contribution of this work, we provide many ideas for code automation for the tool builders. We also release best practices for evolving and maintaining machine learning systems for developers. Developers can adapt them and enhance their code bases. We also provide code examples, so educators can use them to teach the machine learning developers. Most importantly, we provide tools for researchers to statically analyze Python and then machine learning systems. Our framework can mine repetitive changes in any application domain in Python system. It is not limited to machine learning. So but in our research, we instantiated this framework in machine learning systems. We would like to invite researchers, colleagues to build upon our results, and we are looking forward to interacting with you. And then finally, we graciously acknowledge the funding support from NSF and PPI Center. Thank you so much.
Thanks a lot. So is there any author from the last paper that is here to present? Then I'm not entirely sure how to proceed, but I guess we will skip the last presentation. You will find the full 20 minutes video on the conference website. And then I would start the discussion right away. Then there are some questions in the chat, and I think the first question is for Colin. On property-based testing, what would it take to use the approach in a conversational setting where the chatbot and the developer together discover properties?
Take a fair amount more work than what the approach that I explored. So the approach that I explored is known in linguistics and NLP as semantic parsing. Basically, this idea of parsing natural language text into some logical meaning. And in this case, the logical meaning is directly provided by the test. To do this in some kind of conversational setting, you actually need to do some kind of incremental building, an incremental refinement of that logical representation of meaning, which would definitely require some more tooling and some more ideas than what I directly applied.
Okay, thanks a lot. Then we have a question for Emma. I think this is more a reference to a similar paper appeared in TOSM.
Yeah, I just had a quick look. Thank you so much. I'll have it more for a look later. There was the second one as well.
You probably
right?
already mentioned this in the paper. How can software teams make sure that reviewers focus on the most appropriate units of attention?
We don't mention it in the paper, how they can do this. I guess we're just trying to learn at this stage to understand the activity more in this larger study. But we would like to kind of explore different interventions here and maybe follow up with additional focus on specific topics. Like, for instance, coordination could be one aspect. I mean, one thing to do could be to take a specific focus you can have and sort of think about visualizations, integrations, etc., to sort of support that unit of attention. I mean, that's one side of it, but also maybe aspects around coordination, which I guess is connected to the reference in the previous comment as well. I mean, highlighting who's doing what and what do we need to do for change. Definitely limited support for that. You can communicate with words, of course. Ask someone for a review of a specific thing, but it definitely doesn't always happen.
Maybe I can take the chance and connect with a very quick question. Which kind of tools do you have in mind? I mean, is there a specific category of tools that you're aiming to develop?
Well, I mean, so now we're looking at most of the people we interviewed. They typically used Gerrit or GitHub or GitLab in some cases. So we didn't have anyone using Fabricator, but kind of thinking about what it currently looks like, and we're actively building kind of the basis of a prototype, something we can fiddle with, another web-based UI, and then sort of try to new things. I'm also kind of thinking about where should code review happen? Should it happen in this tool over here? Well, you seem to want to be in your IDE over here. So should we be thinking about ways of making this connection easier, either bringing you over here or merging? So thinking more not only in one tool, but maybe how different tools interact and how we can connect these.
Okay, thanks.
Maybe a connecting question on this. Are there maybe any general recommendations that you can already give for people who deal with code reviews on a daily basis to make code reviews more efficient?
I mean, a sweeping general advice would be to communicate a lot. I mean, the tool doesn't always help. So, for instance, it can be difficult to know if someone's busy, and being specific about what you want out of a review. General good, whether the tool supports it or not, I think that helps. So this situation where I explained with the software architect, be sort of implicitly taking on a certain role. Over time, you learn who's doing what. It's when you're new and you don't see the implicit rules. So thinking about how to communicate it, maybe to ramping up new employees, that sort of thing. So communication. But I think tools could do more, but we don't have a specific proposal at this point.
Okay, thank you.
Hey, thanks. Then we have a question for Malinda. This is about dynamic typing in Python and how this is may be affecting your work.
Yeah, that's a very good question. So Python is it's not a statically typed language, so it's a dynamically typed language. All the type informations are available when we. It's a strongly typed language. Therefore, type informations are available at the runtime. So our tools are static analysis tools. So how we overcome this challenge is we use type inference. Type inference is to infer the it's a guess. It's not the actual type of the program. So we guess. We make our best guess based on the information available at the static time. So in our scenario, so we don't use our own tool. We use a type inference tool developed by Google called PyType. So our we experimented with these PyTypes, how it perform, how is our result. So we saw so according to our evaluation, so we saw that PyType does a good job when inferring time information. So yeah, that's how we overcome our problem. So yeah, I think it answers these questions.
Yeah.
Just to add like one thing, even our approach is kind of very syntactic. So the only thing that we actually miss is like the names of those types. But more or less, if you look at our pattern and if you look at how CPAT miner and our adaptation of CPAT miner works, you'll understand that things are very syntactic. So it's not like we're resolving bindings and actually figuring out a very precise graph of how the entire code is dependent on each other. So yeah.
Yeah.
So I don't think that like even if we have more type information, I don't think that it is going to improve our tool in folds. Yeah.
Okay. And have you maybe already done any research on trying to kind of like compare how the same tool in a Java ecosystem works on a Python project? Like, what is the difference between the accuracy in its findings on a Java program versus on a Python program, even if the programs themselves are equivalent?
Yeah, so we adapted refactoring miner. So refactoring miner mines refactoring in Java systems. So we adapted it to Python. So in our Python version, we saw 95% precision, and in Java version, it reports I guess around 98% precision. So precisions in precision wise, refactoring miner almost the same. And then we evaluated the CPAT miner. So CPAT miner, there's a Java version of CPAT miner. It mines the frequently repetitive code changes in Java system. So we adapted it to Python version. We cannot do exact comparison in terms of precision because it's those tools mine patterns in the wild. So there's no we cannot compare the precision, but under the thematic analysis, we perform thematic analysis for both the tools. So it performs well. We didn't do any precision or recall computation, but when we do the thematic analysis, we saw that it finds find meaningful patterns in both the versions. So Python version performed well in comparison to Java version. So those are the two comparisons that we performed. Other than that, we didn't adapt any other tools under this paper. But in the future, we are planning to adapt more tools and make the tools available for the Python systems as well, so that researchers can use them.
Okay.
All right, nice. Thank you for your answer.
Yeah, thank you.
Thanks. I also wanted to go back to Marco's presentation and So it's something I was wondering during your presentation. You have this mechanism to collect security information and well, so to say, retrofit that or have a feedback loop into the DevOps pipeline. Which kind of information can you access to? So which that you can then provide back to the DevOps pipeline.
Actually, that's quite one of the biggest challenges, because as mentioned, the amount of information you require to actually provide beneficial information is rather high. So it's we started our research based on just the automated tools. So tools you normally deploy in a pipeline: static code analysis, secret scanner, vulnerability scanner, hardening checks. In the ops area, some security monitoring and so on. So basically, really hard security facts to a certain degree, as far as you can consider them facts based on things like false positives. But additionally, we also noticed that this is in most cases not sufficient. So we add information, for example, if available, from vulnerability databases like CVE, which is mostly provided by NVD and the information they provide. Additionally, also stuff we do internally within the company. So each company has some threat modeling process or some dedicated selection for threat modeling. And there is a lot of knowledge, and we also need to consider that knowledge in order to improve the information. Consequently, we try to extend it as soon as we receive an information. Okay, this is another pool of information we need to access in order to improve our data. We do exactly that, and that's actually the cool thing about the entire knowledge base, because you can type it accordingly and say, not only now we have a security report here, but we have here an expert opinion, we have here something completely different, and these dynamic rules allow to play with them a little and get the best out of this this whole information, which is, however, also the drawback, because you need some professionals or expert on the field, domain expert, to actually make the most out of this data, because well, this is normally performed by a group of experts for each project or within a project, and consequently, this is also the major drawback of the entire system, that you need some expertise in order to build it up.
So if I understand it correctly, the kind of action that you take based on this information is, for example, to improve the quality of a software component, because you regularly get security alerts from the static analysis tools in the pipeline, so to say.
For example, exactly. This would be an example, or implementing a certain component like an authorization, because you get regular information. Hey, anonymous access is impossible, so please implement this. So these type of recommendations would be given there. Yeah.
Okay. Thanks a lot. So any other question for Marcus?
I have one follow-up. You mentioned having problems with presenting the information to different people. Could you say a bit more about that? How big is the variation, and how, what kinds of, well, maybe an example or something.
The biggest issue is actually how people want to access the information. So a developer is really interested in having it in their default CI environment. So they were really keen on getting these back into their GitLab, GitHub environment as issues, and fixing them there and addressing them there. While we had some project managers, similar product owner in that case, who didn't like that at all. They wanted a typical fancy interface on how to where they could download PDF reports and take them basically to their presentations, where they could show it to upper management or the streamlined management. So this was what we noticed. Consequently, we also changed it and had basically one API, which allowed like an API access, where a developer or technical native person could easily access the information and get the data they required. On the other hand, we also currently develop, or to a certain degree already developed, a web interface in particular for these people that require the visualization, and which want to know, have some graphs or fancy diagrams there.
Okay, Interesting. And it's the same information, just displayed in different views. So you actually aggregate in one case and not the other.
It's basically another view. It's like you have certain queries, and depending on how you query the information, you get different information for your project-specific role, which you then receive, and basically that depends on which role you have within the project.
Okay. Yeah, thank you.
Okay, thanks, Marcus. And any other question on this paper? Otherwise, I wanted to go back to Colin's paper, and because when I saw the title of your paper, I thought, well, this is another language processing work, right? And then you immediately moved away from that and said, no, we use inference and logic. And is natural language processing even applicable in that domain? I mean, would it help? Would it be an alternative?
You mean like what people think of as natural language processing today with machine learning and neural networks?
Yeah, that stuff.
Sure, yeah. I mean, you could totally apply that to this, right? I mean, you could take a sequence-to-sequence model of some kind and train it on, input natural language utterances and output, text for tests, and you'd learn something, right? But of course, one of the challenges there is some of the things I mentioned right at the beginning, which are, if you need to fix how one particular word is handled, you kind of can't. You just have to kind of hope you get enough training data that shows how to do that word correctly, that you can retrain or train further and hope it learns the right thing, or, getting that training data is hard. Right. The flip side there is, of course, there is a big trade-off in terms of where the manual effort lies, right? With one of those approaches, it's all data curation, basically, and a little bit of architecture tuning. The approach that I've taken, there are techniques to learn those lexicons, those rules for what is the individual grammatical role and semantics for individual words. That has been done in computational linguistics and could be adapted here. But what I did was all totally manual, and until I get a little further along with some larger evaluations, that could lead to needing to tweak how certain grammatical categories are given semantics. And without a learning technique, it's pretty high effort. So there's the advantage that the linguists have been doing this stuff for decades. And so there's a lot of stuff there we can use for bootstrapping. But at the moment, sort of different type of manual effort.
Could you combine the two, right?
Probably yes, right? So
I'm not sure what it really means to combine the two, but it sounds
actually. So there's two main ways you could combine it. Like I said, the thing that I'm actually doing is known by the name of semantic parsing. And if you look at like cutting edge semantic parsing techniques in top tier NLP conferences, what you see actually is usually a hybrid of the kind of stuff I'm doing plus a neural network, where it's usually primarily driven by some kind of transformer, some kind of sequence-to-sequence architecture, but trained where the output is actually constrained according to some formal model of grammar along the lines of the stuff that I've been working with. So, I mean, long term, I think the right answer is you need pieces of both, but you do need both.
Okay, thanks a lot. Any other question for Colin?
Yeah, maybe one. So the work that you do, was it focused on finding the properties, or did you also look at supporting the generator? If there are domain specific,
it's everything, right? So it's literally writing things like if you type in every integer as an integer, you get for all generated integers, the result is an integer. So
could there be domain specific types?
You can do that if you are willing to extend the lexicon, right? And so this is one of the places the manual effort comes in right now. And long term, one of the places where you'd eventually want to learn from a small number of examples.
So,
But it does subsume both the generator and the property.
and if the data are like objects or records with some fields, right now what would the natural allowed here? What would the natural language equivalent be of that?
I mean, this is one of the places where there's sort of room to go in a few different directions in terms of semantics, right? So something I didn't get into is if you look at that classic linguistics work, there's actually a wide variety of approaches to what is the denotation of an adjective, what is the denotation of a noun phrase, and sort of longer term, one of the questions that I still need to answer is one of those approaches going to be better than another for describing things like, once we get into examples, talking about specific fields and things of that sort. So the properties from the draft testing textbook that I looked at were all mostly high-level input-output properties. They weren't getting quite to the level of detail of talking about, well, in the output, this field has this property and this other field has this other property. We know grammatically the toolbox I'm using can do that, but I haven't pushed in that direction yet.
Okay, thanks. Yeah.
Thanks. So I have a question for Bart and this idea of project smells. How much? So I find it really interesting. How much can you, or would it make sense to move from, let's say, technical smells, for example, configuration issues, to proper, so to say, project management smells? So things that also take into account the, I don't know how to formulate that, for example, time of decisions or events that may happen. Does it even make sense? Is it a thing?
Yes, I think that definitely does make sense. A lot of the software engineering for ML best practices, SE for ML best practices that I looked at, and also Google's rules for ML, actually have some rules that relate to how, as a team, you manage your project and things like governance. Where do you store your data, or is it ethically balanced? Stuff like that, and that is, I do have to say, that is really difficult to analyze, to get to know based on the project's source code. So MLint tried to focus mainly on what can we figure out in terms of project smells based on the code repository of the project and the tools that they have configured within there. But things like how you manage your project as a team, that isn't generally saved in a repository, and I guess further research would be required to see how you could capture that in a format that where it is possible to actually analyze those in some kind of an automated way.
Wondering, well, somehow commits tell you something, right? Because they have a date, they sort of how things are working, who is doing the commit. It's obviously not much. But yeah, source of information would be the issue. But I think that this would be really interesting. Yeah,
I think definitely commit messages could be interesting, even if your first recommendation is just going to be improve your commit messages, be clearer about what you actually do when you commit code. Otherwise, maybe there is indeed interesting information in that. Maybe you can even tell something by the timeline between commits. Like if it takes 3 months to make another commit, and apparently the project was put on hold or something.
Okay. Thanks a lot. Any other urgent question for any of the speakers? If not, it's 17:59 here, and I think this is the perfect timing to conclude this session. So thanks, everybody.